Okay, so for people, yeah, okay, got it. It's fine. For people who spend time on Canvas, was the recording and the stuff useful or any feedback? Did you guys look up the recording from last lecture? And I also tried to put a lot of resources, so you ask, Okay, so far so good. You may not be done with everything I put there. You have time, okay? Today we have a lecture. Thursday we have a guest speaker. So by next week, try to be done with your linear algebra review. If you're not already done with everything on Canvas, don't worry. There was a lot of stuff there. It's okay. You have time. Some of it you can even do later. It's all right. So yeah, let's start with some hands-on work a little bit. So we defined this like norms last time. There was this Euclidean norm that we are used to, and there was this L1 norm. And I said you could also define it with any p if you like, but you will usually use 1, 2, or infinity. That's all. And infinity means take the maximum among the coordinates, okay? And just to make it concrete, let's try to do some example. We don't have to do everything I wrote here. Maybe let me even erase some of it. So I'm going to define a couple of sets here. And then your task will be to try to look at them and see which one is included in which. Okay, let's just leave 3 of them. And the first set is like, I'm working with vectors, which has 100 features, all right? And then the first one says everybody who has L1 norm less than 10. Second set, everybody who has L2 norm less than 1. And the last one says everybody who's got infinity norm less than 1 over 10. Okay, now think about it, maybe 30 seconds or a minute, or maybe a little more, to see which set is included in which. Which one is, maybe, I'm not saying, double check. Maybe they are not nested, think about it a little bit. Just to refresh these definitions and because I remember there was a very good question saying, which of these norms are more sensitive to errors, for example? It depends on how you set it up. And I'm trying to illustrate it a little bit. So which set looks bigger, or are they nested? Maybe not. Play with it a little bit, right? Think about it. Let's start from here. And I could walk around and take any questions. Meanwhile. So the last one, at least to me, like kind of easy to think about, every coordinate. So what does this mean? X infinity less than 1 over 10. That means max is less than 1 over 10. If the biggest coordinate is less than 1 over 10, that means like every single coordinate is less than 1 over 10. So for example, try to compare this one with the other two. Yes, Adam. This is literally the unit circle for this norm. Yeah. So I'm trying to ask you, is S3, for example, included in S2 as a set or not? Or how does it look? Okay. Yeah, it's fine. What do you think? Okay, we have our first guess. And it's always nice to debunk people's guesses. So if you have a counterexample, go for it. All right, just kidding. Okay, S3, you said? So this is our first guess. I do not know. Mhm. Yeah. Yeah. In 2, you should make it like 1 over 2. Yeah. Yeah. So that would be hard to draw, but I'll try my best. So what Farhan is saying is this. If I try to think about like 2D version of this, But then you have to correct the numbers as such. Instead of 1/10, then you will have to have the correct number for 2. Okay. But anyway, so let's maybe get going a little bit. So like, what is S3? It says x infinity is less than 100, right? Less than 1/10, I'm sorry. What is x infinity? Maximum among the coordinates. Well, if the max is less than 1/10, that means every single one is less than 1/10. So you're looking at a vector. Let's say this is 0, 0, 0, okay? How is your vector going to look like? Like in any direction, it could go at most 1/10, right? So maybe that's what you meant when you were saying, I'm trying to picture it with 2D. Yeah, maybe that's, yeah, exactly. It's like in every direction, I could go at most, say, 1/10. Yeah, too small writing. Let me try to make it better. Yeah. So let's say this is 0. I'm trying to make a visual of set S3. It's going in any direction at most 1/10. Let's say for now, this is 1/10, okay? Okay, good. And then this is S3. And how about S2? Or maybe S1, even easier. What is S1 saying? L1 less than 10. What was L1? Let me remember the definition. I sum up all the coordinates, right? There's like 100 of them. I'm working with vectors, suppose in this application with 100 features. Okay. So if you sum up 100 numbers, where every single one of them is less than 1/10, what do you get at most? 1/10, 100 times, 100/10, at most 10. So that means everybody here for sure satisfies the condition in the first set. Okay, so if you sum up all those coordinates and every single coordinate is less than 1/10, and there's 100 of them, what is 100 times this number? 100 times 1/10, 10. That means everybody here is going to be in S1 for sure. So at least S3 is included in S1. That's for sure. This I don't know. We have to check. Okay, right? So we need to think about this a little bit. All I'm trying to say is like a priori, when you don't think about the numbers here, 10, 1, and 1/10, it changed the game. If somebody would ask you, I have like a unit ball and a unit cube. Of course, you could put the ball inside the cube, right? Cube is better, bigger. But here, the trick is like the cube is not unit cube anymore. They made it 1/10. So now you're putting a smaller cube inside the ball, actually, right? So that's what's going on. So depending on whatever you're working on, the way you set it up and what it means might change. There is not like a rule of thumb that one norm is more sensitive than the other. It will change depending on how you define. That's why I wanted to make like a small example with you at the beginning. Okay, so this is recorded. Go back to it because it will take a couple of minutes before you figure out, and I don't want to spend say 5-10 minutes of the lecture with this. Okay, right? Go back to it and work on it. I hope it's a good illustration. All right. Okay. All right. That was the first kind of quick warm up, and I want to do one more warm up. Do you guys remember your Pythagorean theorem? Like a squared plus b squared equals c squared from, I don't know, when did you first see it? High school or maybe some even middle school, depending on the schools you had, So, but they taught me, at least when I saw it first, on the plane, right? So they told me like there was this triangle, Pythagorean, right? Something like this. Usually the picture was better than what I just did. So I got better teachers than myself. So something like this, right? So don't write this, but we are going to do the same thing, not on literally plane, but the same story holds actually in whatever dimensions. That's what I'm just going to tell you now, okay? All right, so let's look at the Pythagorean stuff, not necessarily in plane, but in more dimensions, okay? So here's how is the story is going to go. I got 3 vectors, x, y, and z, and they live in somewhere, Rn, okay? And I got an inner product. Is inner product, you can think about it literally just a dot product, but there could be many ways to define an inner product. As we said last lecture, I'll get back to it again this lecture, but as soon as you have an inner product, you have a notion of an angle. That was what we said last time, right? So if dot product of two vectors is 0, they are like orthogonal to each other, okay? As soon as I got an inner product, I can say x minus y is orthogonal to z minus y. Okay, that makes sense as soon as I have an inner product. So what is it saying is this. I got some, let me try to picture this. Let's say here is x, and here is y, and x minus y is something like this, and z minus y is something like that. And apparently they are orthogonal to each other, okay? There's like a right angle in between. And what else I know? X minus y's norm is apparently 3. Again, the norm I'm talking about is given by whatever inner product I was using. As soon as you have the inner product, you have a norm, you have angles, everything is set up for you, okay? For us, dot product is the Euclidean norm, for example, okay? This happens to be 3, this happens to be 4, and the question is, what is the length of this guy? Z minus x, or x minus z. Any guesses? Yeah, 5, right? So 3 squared plus 4 squared is 25, which is square root of 5. So yeah, so the Pythagorean theorem works even in whatever dimensions you have, as soon as you have a right angle. So this guy will have length 5, okay? So computing the 5 is not the main point here. The main point is, as soon as you have the orthogonality or right angle, or sometimes they say perpendicular, you know, if you're doing LaTeX, you'll write perp for this, right? So the same Pythagorean a squared plus b squared still holds, okay? And this has, you know, much more consequences than I could have imagined. So just off of this today, hopefully we will talk about, say, linear regression. As soon as you understand this, you kind of get very close to understanding linear regression. Okay, so this thing is simple, but it's very useful, right? Okay, very good. Now, before maybe we move on, one more small fact you guys probably all aware of. Let's say I have a line here, like this, and I have a dot right there. Let's call this dot x, okay? And let's say on the line, I pick the closest point to x, okay? Let's say this point is y, and property of y is this. Y is the closest point to x on the line. Okay, now let's look at this vector here. Going from this y to x. What do you think the angle between this vector and the line would be? What would be the angle right here? Any guesses? Right angle, 90 degrees pi over 2. It's going to be orthogonal. That's what the answer was. And why? Well, if this is orthogonal, it would make sense. Why? Let's say, let me pick another point. Let's say z, right? And let's see if this z could be closer to x than y. Well, look at the distance in between. You will have your Pythagorean theorem, right? X to z, this distance, is always going to be bigger than this guy. So to make the distance smallest, looks like, we just need to find the right angles. That's about it, okay? And if this line is, suppose, what your computer is able to compute, and if this x is your reality, your model, okay, will say y instead of x. That's the basic idea we keep using all over the place. You set up some model that you can compute somewhat quickly. Well, before we had this whatever billion parameter models taking over the world, okay. So if you want to do something efficiently, okay, you set up a model that you know you can compute efficiently, and then within that model, you will try your best approximation to actual reality, okay? And this is going to be a basic fact coming back to you all the time. Let's say this line will be what you can compute quick. this is what you actually want to go for, then you will say, okay, I'll go with Y. That's the best I could do quickly, right? So far, so good. Okay, now let's go to today's discussion. So last time we started reviewing linear algebra. We talked about vectors, matrices, and norms on vectors, that kind of stuff. Let me go back a little bit, recap, and move forward. So we talked about, say, eigenvalues, right? What was an eigenvalue? Eigenvalue was the solution of this equation. A times x equals lambda times x. This thing is called an eigenvalue, and this thing is called an eigenvector, right? And then we talked about like using all the eigenvectors like a basis if possible, things like that. And then the one nice case was when we have symmetric matrices. So before I say anything else, these eigenvalues could be even complex numbers, right? So all we know at the beginning, for every n by n matrix, you will have n complex eigenvalues. But we usually would like to deal with real numbers instead of imaginary numbers. If your matrix is symmetric, then all eigenvalues become real, okay? What is symmetric? A transpose should be same thing as A, okay? So do you remember the transpose? You take the matrix, you turn it around. If you turn it around, it still looks exactly the same. That's a symmetric matrix, okay? In that case, all the eigenvalues are real. So we deal with real numbers, bless you. And there's even better stuff. We did some math. We realized in that case, if you have two different eigenvectors, x and y, corresponding to different eigenvalues, x inner product y is always 0. Eigenvectors are always orthogonal to each other when your matrix is symmetric. So it looks like quite nice. Now I got real eigenvalues. My eigenvectors are orthogonal, looking nice. You know, what could I do with this? Well, one thing you could try to do, instead of operating with your usual bases, like, you know, we use usually what? This E1, E2, E3, that kind of basis, right? First coordinate 1, 0, 0, 0. Then what is our standard basis, say? This one. Let me write, then I'll erase. If I do nothing, that's usually what we use, right? 1, 0, 0, say 0, 1. This type of stuff is our standard basis, right? But let's say instead of that, can I use the eigenvectors as a basis? Can I do a change of basis? Maybe things will get easier, maybe. Let's see if that happens or not, okay? So what I would like to do is this. This is my matrix A. It's symmetric. It's got eigenvectors ui, u1, u2, un, and eigenvalues lambda 1, lambda 2, lambda, okay? A times ui is lambda I times ui, right? And I could stack up all those eigenvectors next to each other. This is the first column, this is the second column, third column, etc. And what I know, all these eigenvectors, they are orthogonal to each other. And if you take the same thing twice, you make it like norm 1, okay? So if you take inner product u1, u1, assume it's 1. If you take u1, u2, 0, okay? Now, let me say take a vector x. It's in like usual basis. And I want to put this guy into my u basis, my eigenbasis. What I want to do is like I want to write x in terms of this u stuff. First Lego, first building blocks times a number. Second times the number. You know, I want to do this. But this, you know, maybe it looks a lot of work for the moment, but don't worry, how do you find those alpha stuff? Just for now, bear with me to see what's going to happen if you can do that, okay? Then let's say I take this x, I act on it with my matrix A, okay? Then let's try to follow what happens. Since x is equal to this u stuff, it's the same thing as your A acting on that u stuff, right? A times all that stuff. Okay, now what's next? You're going to keep decomposing. Ax equals A times alpha 1 times u1. Here, u1 is a vector, alpha 1 is a number, but I know what is A times u1 precisely. What was it? It's an eigenvector. A times u1 is lambda 1 times u1. This u1 is a very special vector, right? So what happens is, if you go next, write the decomposition, literally Ax becomes alpha 1 times lambda 1 times u1, blah, blah, blah. Long story short, in U bases, X started out with alpha 1, alpha 2, alpha n. That's how it started out, like this. And in the end, after A hit that vector X, it ended up becoming lambda 1 times alpha 1, lambda 2 times alpha 2, lambda n times alpha n. So if you put stuff in U bases, what your matrix does is very transparent. It just takes every coordinate, multiplies with those eigenvalues. That's it. Okay. So it acts like a diagonal matrix in those U bases. Okay. So another, fancy way to talk about the same thing is like in eigenbases, your matrix A starts looking like just this. Take the first coordinate multiplied with this, second coordinate with this. It becomes rather simplified, right? Very good. And the way you would see this written in books, it's going to look like this. A, you will see equal to U, this thing right there, U inverse. Okay, that's what you will see in the books. What's going on is like this first guy taking the X, turning it into U bases, turning it from the standard to U, and then this thing in the middle is just stretching and scaling, and U comes back and puts it back to where it started from. But you don't have to remember this on top of your head. Just remember the meaning, okay? It's take an X in standard bases or some other bases, put it into eigenbases with some operation. Then after you put it the eigenbases, your matrix starts looking like just like the diagonal guy. Do your diagonal, put it back, okay? So when you are able to do this, it's like, okay, super nice. It's like just like a diagonal stuff. Take every coordinate, multiply it with that eigenvalues, done, okay? Of course, not everything goes as easy as this one. And also, moreover, I skipped over like the questions of how do I even compute this U and this lambda stuff, okay? If you have all that, this is how it looks, okay? But of course, somebody will hand you the A. They're not going to hand you all the eigenvalues and the eigenvectors, right? But knowing this is very useful. And we will do variations of this today. Okay, so far so good. I only told you what's an eigenvalue once again. And when you have a symmetric matrix, things are kind of nice. And let's see what's next for us. And you have this little exercise on Canvas. You maybe did it, maybe are going to work on it. But let me remind you this in terms of its conceptual meaning. This U matrix right there, let me write it again. This eigenbasis matrix, U, it was like U1, U2, UN right here. And if you take U transpose, it's going to look like this column will become a row, right? And if you do U transpose U, what does that mean? It means take the row here, multiplied with the first column here, right? When you're multiplying two matrices, how does that go? Let me maybe change the order of the matrices to make it more transparent. Let me put U to the right and U transpose to the left. Very good. Now think about multiplying this matrix with that matrix. How that's going to go. You're going to take the first row, multiply it with the first column. What is U1 times U1? 1, right? Very good. How about the second step? You're going to take the first row again, but this time you're going to multiply it with the second column. But they were orthogonal. U1 times U2, 0. And it's going to keep going that way. So ultimately, you will literally get the identity matrix out of this process, okay? You're just going to see 1, 1, 1 on the diagonal, 0 everywhere else. And this type of matrices have a special meaning. And this was the point of the exercise. It's also on Canvas. They only move stuff around when you act on a vector with this kind of matrix. It doesn't stretch or squeeze. It doesn't change any angles. It just rotates stuff, okay? That's what they do. For example, if you give it an X, U times X will have the same norm as X. Nothing is going to change in terms of how big is the vector, okay? Yes. Yeah. Exactly. And there's even more, which was not written in the exercise here. If you have two vectors, and if you look at the angle between before and after, it's going to be the same again. Okay? It doesn't only preserve how big are stuff, it only also preserves the angle between stuff. So literally it's taking stuff and just rotating them. When you rotate things, they don't get bigger or smaller, and the angles between stuff doesn't change. Okay? Yes. No, their eigenvalues are just 1 and -1. They're very simple. So this type of matrix is only rotating things around. Okay? Just think about it in a modular way. Whenever you see a matrix of this sort, you just think about, okay, this is just rotating my vectors. That's all. Okay? So it's like I gave an exercise on Canvas where you were supposed to find the matrix that corresponds on the plane, take stuff, move it counterclockwise 45 degrees. When you compute that matrix, you're going to see something like this sort, for example. Okay? Yes. Okay, I think we can discuss this offline. Okay, yeah, good. So far I was thinking about eigenvalues of this guy, but that's not the point here. So this is a simple guy. If you see a matrix that is orthogonal, which means transpose is its inverse. Transpose times the guy's identity, right? That's the definition of inverse. Transpose happens to be the inverse also. This is a nice and simple guy. All it does is it takes your vectors, rotates them with some angle. As soon as you see this, think about rotation, okay? It's a modular operation. And we will decompose more complicated stuff into pieces like this and something else. Okay. All right. Very good. Okay. Now, I was happy with this nice symmetric matrix looking like diagonal and stuff. But of course, that doesn't always happen. If my matrix is not symmetric, what could I do? Okay. That's so that I could still understand somewhat transparently. So there, the notion of singular values come. If your matrix is not symmetric, let's say your matrix is A, if you multiply it with A transpose and get a matrix X, do you think this X will be symmetric or not? Well, to check, take its transpose. X transpose will be transpose of the first, A. Okay, let me write small rule for you to remember transposes. If you have your, say, matrix X, Y times Z, then X transpose is Z transpose times Y transpose, if you forget this, okay? When you do transposes, the order changes. So look at the transpose of this guy. Second one will get transposed. This guy will get transposed. I got the exact same thing back, okay? So it turns out this is a symmetric matrix. So it is symmetric, so it's got nice real eigenvalues. Maybe can I use the eigenvalues of this more complicated looking guy to understand my first A, okay? And that actually works out. And what you get out of it is called the singular value decomposition. And it goes like this. Every matrix, even if it is not square, even if it is M by N, okay, will be decomposed into 3 pieces. The piece in the middle is diagonal, and the piece on the left and the right are just rotating stuff. Okay, so you can take any matrix, and you'll be able to write it as multiplication of 3 pieces. First piece rotates stuff. Second piece diagonal. Third piece rotated again. Okay, so let me show you a picture of this that I showed, I think, in the last lecture. So it's looking like this. This is where I started off. And my A matrix was doing some stuff on them. It was not so easy to understand. When you decompose it into 3 pieces, the first piece go from here to some rotation. Then diagonal means stretching or squeezing. So diagonal, for example, stretching this guy by sigma 1 number, this guy by sigma 2. It's like pressing it. And then the other one rotates it back again to somewhere. That's what every single matrix does, okay? Now try to imagine if this sigma 2 would be 0, what would happen? Go for it. I think Owen was the name. Okay. Tell me I think you see it, but tell me the imagination. It's like gonna be, yeah, it's gonna be like flat, right? So if the sigma 2 is 0, just flat. That means this matrix is actually killing some stuff, right? You gave it a 2D thing, and if sigma 2 would be 0, it's just making it 1D. Now this can actually happen. Some matrices project stuff down. And we are gonna talk about them today, okay? Yes. It wouldn't be invertible then, exactly. So if it is, negative is possibly invertible, but very good question. Now, Owen is asking, can I ever get the singular values negative, right? For example, eigenvalues can be negative, but singular values is always positive or 0. And I'll tell you why, okay? Singular value decomposition will never give you something negative. Very good question. Otherwise, how would I imagine this guy being like stretched negative number much, right? So it's gonna be crazy. Yeah, very good. Very good point. Singular value decomposition always gives you either a positive number or a 0. Okay. All right. So here is singular value decomposition. So it's going to look like A equals some matrix times another one times another one. These two guys are just rotation. If A is M by N, the first one is an M by M orthogonal guy. The second one is an N by N orthogonal guy. And the thing in the middle, the sigma, will be giving you all the singular values. And they are either a positive number or a 0, okay? And usually the convention is they will start from the biggest one and line them up until the smallest one. And if you have a 0, of course, that's gonna be the smallest one, okay? And whenever you have a 0, that means your matrix is not invertible. And that's fine. Sometimes it's very useful, actually, okay? And now, why on earth I always have the singular values non-negative? It's actually because of the way it's constructed. I don't know how much time I want to spend on this. Let me see. Well, maybe quickly, if you just look at here, AX inner product AX is by definition this guy. And A goes to right-hand side as A transpose. And this is what we were talking about, right? And now think about the eigenvalues of this guy. Let's say one of those eigenvalues is lambda, and X is then say eigenvector, okay? And this guy will be lambda times X. And I can take that lambda out. Lambda times X, which is nothing but X squared, is supposed to be AX squared. Well, this is a positive number. This is a positive number. Then this guy got to be a positive number too, okay? So all eigenvalues of this A transpose A type matrices, they are either non-negative, they are either positive or 0, right? Yeah. So this singular value. Yeah. That's the part one needs to actually go through and prove to you, which I don't want to do today, okay? You just need to, I'm just telling you what it is. So A transpose A's eigenvalues are the singular values of your own matrix. And by some math magic, that means your matrix A is literally this guy. Okay? Yeah, we want to do diagonalization, but it's not working out as we want to. In diagonalization, we would like this U and V to be the same thing. Let me go back to a symmetric matrix case. Right here. You see, I got the same thing back. And in the middle, I got a diagonal. That's the nicest possible case. Okay, by same, I mean the inverse, okay? But in the singular value decomposition, you don't get the same thing back. You get different U and V. It's not as good as diagonalization, but almost there, okay? U and V are two orthogonal matrices. And they could even have different dimensions. Okay, so it's like the directions where your matrix is kind of becoming transparent. Think about it that way. Let's say the first vector of this guy is corresponding to first singular value, right? Sigma 1 is going to correspond to first thing here. That means like that direction is where your matrix is the most dominant, for example. Okay, let's go back to the picture. you have V1 and V2. These are the two directions. And now we multiply it with V transpose. Since it is orthogonal, V1, V2, it gives you the V. That's why the picture is set up that way. So V will be V1, V2, okay? And then you multiply this V with V transpose, you get identity. And then you do your singular value stuff, and you act with U, that's where you end up. So your matrix in this direction is doing the biggest change. It's sending it to sigma 1 much stretched, but you don't get V1 times sigma 1 because it's not literally diagonalization. You get sigma 1 times another vector U, okay? So this U and V tells you the axes. Your matrix is doing either the most change or the little change. This kind of literally tells you what the matrix is doing, okay? I don't know if it answers your question, but I tried my best approximation. Okay, all right. So that's what singular value decomposition is. And in this course, of course, we want to use it for some algorithmic purposes. For now, let me see if there is anything else. Any other questions from anybody about what is singular value decomposition? And this picture corresponds to the case where the matrix is not like killing anything, it's invertible. And now we are also going to talk about when the thing is not invertible after I wait and see if there are any questions. So far, so good? Okay. Okay. So now let's think about the case where my matrix is actually making like sigma to 0, like killing some stuff, okay? And we are going to make some use of it. So what do I mean by that? Those kind of matrices are called projections. Imagine you're looking at the shadow of an image. You're looking from 3D to 2D. And that could be modeled by a matrix. And the word on the street for this is PCA. Okay, so you look at something in a higher dimension, and you project it down using a matrix, and you project it somewhat cleverly. That's called principal component analysis. Of course, I'll make it more precise. I'll not say, okay, I covered PCA, now I move on. That's not going to happen. I'll tell you more. We also have a very nice notebook about PCA. I'll put it on Canvas today. But let me talk about the case where you're actually projecting down, right? So what do you mean by projection? Let me tell you more cleanly. If a matrix A satisfies the following, A squared is the same thing as A, then that's a projection. In other words, you take a matrix, you take a vector X, you do something on it with A, you do the A again, nothing happens. AX is the same thing as A squared X, then that's a projection. In the picture above, suppose my projection was taking stuff from 3D and putting down onto 2D. After I arrive to 2D, if I do it again, nothing changes. I'm already on 2D, okay? That's a precise way of saying a projection. Right? So whichever way you prefer, keep that in mind. Some people like the algebraic clean way. Some people like the visual way. Keep whatever way you like. Yes, go ahead. Kind of, yeah. Yeah, yes, exactly. So whatever is your correct mental picture, keep it for yourself. That I like that one very much. So some people learn geometrically, some people algebraically, whichever way works for you, use it, right? So exactly. If you kill the dimension, you cannot kill it again, for example. I like that. All right, that's what a projection is. And now here's a standard example of a projection. Let's say I got two vectors in 3D, y1 and y2. And I look at their span. Let me try to draw. Let's say y1 and y2 are here, okay? Imagine them like this. And this H is the whole like plane. Stuff I could create using y1 and y2, okay? Span of y1 and y2. Span of these two vectors is the whole thing, suppose. Does it make sense? If you take two vectors, their span will be a two-dimensional thing. And that two-dimensional thing is sitting in 3D. And now you take a point X, and you want to project it down on that two-dimensional thing. Okay, that projection is going to be represented by a matrix A. And now I want to know, like, how do I compute that A, right? It's a projection, clearly. I'm going from 3D to 2D. Moreover, since this is a projection, what do I know about this A times X? Can I go ahead and claim this should be the closest point on this H to my X? You think? It's the projection. If something is closer, could that be the projection? Or like maybe about angles. Maybe we can go through angle route. Like let's say I pick another dot on this H, Z. And let's look at this vector. Look at the vector up to my X. Do you think you'll see right angle here or not? Well, the right angle is given to you by the Pythagorean theorem, actually, right? If you look at the distance from X to Z, that's going to be this squared plus this squared. That means that is going to be bigger. Okay, so we observe two things now. I'm going to have this right angle. And second, AX is the closest point to my X within this plane. Okay, so let me write this out. The projection AX is the closest to X in H. And if I have any other Z in H, then X minus AX vector should be orthogonal to Z minus AX. Okay. And, you know, because of this, sometimes this is also called orthogonal projection. Okay. Now, I still did not answer the question of like, how do I even compute that A? I'm trying to understand what it is doing. But, you know, I still didn't get to the point like, okay, I gave you two vectors, y1 and y2, give me my A, right? That's what we want to do, right? Okay. Now, let me maybe play with this a little bit. So far, so good. Any questions? Using these properties, I'll get a way to compute it. That's why I'm, of course, talking about it. Yeah. To be like no. Exactly. So that's why I put like any y1 and y2. So this, if basis, let's say basis corresponds to just this, it would be also like that, sitting in 3D like this. Exactly. Yeah. Just projection. You could even project on not planes, on more complicated stuff also. Projection means like getting my best approximation within what I can compute quickly. Think about it that. All right. You can even project on, say, this. That's, for example, is the basis of a lot of convex optimization based algorithms. We may touch upon sometime this course, we'll see. Okay. Anyway, so let's get back to here. Very good question. Thank you. So let's say, you know, I have these two vectors, suppose 1, 1, 0, 1, minus 1, 0. Like, I want to project some stuff on their span, some x, you know, and find the, you know, AX will be the projection, right? Like, go find that A. Well, you know, AX is going to make X written in terms of this Y1 and Y2. So it's going to be something like this. If I put these two Y vectors together, and if I have a vector, say W, this projection is going to make X in terms of this. Well, I kind of have to find this best W right now. I did not solve the problem. I just made another words for the same problem. Or any other attitude, like any other approach to solve this problem. That was my idea when I was, first idea that came to my mind when I was writing this. Like, how would you try to find that A? I know, let's say Y is what? 3x2 matrix now? If I do Y transpose, it'll be like, sorry, this is a +1. How about like Y transpose X? Would that work? Like what I'm trying to say is just use a y transpose. Would that work? Well, it's not a bad idea. It doesn't do the trick fully, okay? If I would have two vectors that are already nice and orthogonal to each other, then y transpose would already do the trick, okay? So if your vectors would be like 1, 0, and 0, 1, for example, then you will be already done with y transpose. But they are not orthogonal to each other. Or maybe they are. Okay. Anyway, so this doesn't look so easy, basically. That's my point. So you need some sort of orthogonality. And one way to get about it is this, by the way, you can solve by hand, and it's not a bad exercise. But there is a known way to solve this issue, which goes by the name QR decomposition. We already have a Jupyter notebook about this kind of stuff on our canvas. When you get time, look at that notebook if you did not already. So that notebook was going through some decompositions that we will use. Yes. Okay, no worries. So that if anybody doesn't like Jupyter notebooks, I feel for you. Okay, somehow they became the standard way. That's why we are doing it. All right. But if you're somebody who likes to do your stuff on terminal, you might hate Jupyter notebooks, which I have no objections. Okay, so but that's what we are going to do throughout the course. I will put Jupyter notebooks. Somehow it became standard. Don't worry, I'll help you out with that. Anyways, no worries, I'll show you. That's easy. Not a problem. All right, let's get back. So, but all I'm trying to say is I understand anyone who has any objections to Jupyter notebooks. Anyway, let's get back. So there is something called QR decomposition that's going to help us a lot with this projection question and many other things. What's that? You can take any matrix, and ideally you would like to make it look like, something orthogonal times something simple, if you can. Because orthogonality, at least in this eigenbasis world or singular value decomposition, was helping us a lot. And then the thing that gets closest is this QR decomposition. What is it? You can take any matrix and write it as Q times R, where Q is an orthogonal one, and R is an upper triangular one, okay? If your matrix is M by N, this Q will be M by N, and Q transpose Q will be identity N, and this R will be N by N. And if your matrix has full rank, you will just see something like in the upper triangular. If it has rank less than N, there will be 0 black here, okay? So if your matrix Y has rank N, your triangular part will look nice. It will be like this. But if it has, say, N minus 2, there will be 2 lines here, just literally 0, nothing else, okay? All right, so that's called QR decomposition. And now we are going to use it to solve our projection problem, all right? But let's go slow. Let's not solve projection directly. Let me solve an easier problem first. Suppose somebody already gives you something that is inside that plane, okay? Let's say I have this H right here. So suppose I'm going to try to solve this problem. I have my H. And H is given by span of couple of vectors. Y1, Y2, Yn, I'm sorry. And all these vectors are living in, say, Rm. Okay. And in this H case, maybe I have only 2 to make it look like H. Okay. And then what I want is like somebody gives me, say, a point that is already here. Okay. And they ask me, okay, write your X in terms of this Y stuff. Like X is like some weight times Y1 and some other weight times Y2. We know that it's in the span, but what are those weights? Compute them for me, okay? Let's say this is the problem we want to solve first before going for projection, right? So far, so good. So this corresponds to the following equation. I want to solve Y times the W equals to X. Yes. You'll get there in the next step. Yes. We are going to go, in 2 steps, not just right up. Suppose it's on the plane, and I want to find these numbers that makes me able to write this X in terms of Y1 and Y2. How do I do that? Okay. That's the first question I want to solve. Then we will get to what you just said. Okay. Let me get the pictures a little out. And I want to just write this question a little better. So here Y is M by N, and it is given by this vectors. And this weight vector omega or W is weight is living in Rn. And somebody gave me an X that is in Rm. However, it's in the span of this Y vectors, okay? M is bigger than N, imagine. You may not necessarily be in the span. Maybe M is, say, 3, and N is 2. So my X doesn't have to be in the plane, but suppose it is. And I'm trying to solve the equation Y times Y equals X. Okay? And let's say I did QR on this Y matrix. Now this is what I'm trying to solve, right? Q times R times this omega or W is X. Let's multiply everybody by Q transpose. What is Q transpose Q? Identity by definition. So that goes away. So I have R times W equals Q transpose X. And as I said, if your matrix is full rank, if it is rank N, this R in that case will be an upper triangular matrix that looks like this, like everything here is written and here there's a 0. And in that case, that R is going to be invertible. So then you will get W equals R inverse Q transpose X, right? I multiply left and right with R inverse. Okay. Let me write this again because I see people getting tired. Let me write it. So it will be R inverse R So in other words, what I got so far is omega is R transpose R inverse Q transpose X. Okay? Yeah. Not always if it is full rank, yes. Yeah, exactly. Very good. And then I was looking at Y times omega to be equal to my X. Now let me put back QR in terms of Y. It will be QR R inverse Q transpose X. I'm almost done. Thank you for patience. R and R inverse kills each other. You end up getting QR omega, which is Y times omega, same thing as Q transpose X. And that's where I wanted to get it. When you know Q and R, turns out all you need to do is Q transpose X. That's your projection. When you need projection. If you're already in the span, that's what you have. Okay? All right. So in general, what's going to happen is this. Not only if you're in the span, even if you're trying to project, when we know QR, to get that A matrix, all we are going to have to do will be Q times Q transpose. That's going to solve our projection problem. Okay? So I did this only in the case when you're in the span, but the same thing works out even if you're not in the span. Okay? So the punchline of this is going to be the following. I'm trying to give you the intuition why it is true. Okay? When you're trying to project, When you're trying to find that A matrix, it's going to be Q transpose. So let me get back here and put this in the place I was asking. For example, here, this is your Y matrix, your vectors, okay? You'll need to find QR decomposition of this matrix. You will write as Q times R. And then the projection A will be given by Q transpose. That's it, okay? All you need to do, stack up your vectors like a matrix, do the QR decomposition, which is already implemented in whatever favorite programming language you're using. Take that Q times Q transpose is your projection, okay? Yes. So the point is, this Q is an orthogonal matrix. What is the property of orthogonal matrices? If I wouldn't do Q transpose, but if I would be doing Q transpose Q, that will be the identity, right? And that identity means those vectors are orthogonal to each other, and every one has norm 1. So it's almost getting there, but not being able to do that fully, yes. So what you're doing is this, you're taking your matrix Y, and you're decomposing it into 2 pieces, orthogonal piece here, upper triangular piece here, that's it, okay? So QR is orthogonal times triangular. That's how you could kind of visualize it over here. Very good. Also, if you have heard of something like Gram-Schmidt decomposition in your linear algebra course, that's literally what this is, just in a more algorithmic way. If you did not hear about it, forget about it. But that's fine. I'm just trying to connect it to stuff maybe you have seen or not. So at the end of the day, projection problem is solved by QR decomposition. That's the punchline. And how do you compute QR? I'm not going to get into that part. This is something people have worked on for decades. Numerical linear algebra is the field that deals with this type of problems. Does linear algebra with numerical computation. And it may be one of the most developed parts of computational science. Still being developed because it's so crucial. And QR decomposition is a stable algorithm. We have stable algorithms for this problem. Okay? You don't need to even only solve the problem numerically, you also need stability. You know, maybe you solve it, but there is so much numerical error, it might become garbage. Have you heard of this thing called quantization? These days, it became so popular in machine learning. Anybody? Or let me maybe even go back. Have you guys heard of floating point IEEE 332 standards? Right, this everybody's heard of. So, you know, we did not have those standards back in the day. It was a huge deal, right? The guy who created MATLAB, Claire, what was his name? I always forget this. Whenever people visit him from Europe, he used to tell them 2 things you have to see in this country. Go to Grand Canyon and go to, floating point arithmetic standard meetings. That was such a big deal at the time. Now we have it, we rely on it. But if you're doing, say, quantum computing, we don't have those standards now. We are back to those days, right? Okay. So now what people are trying to do in some machine learning stuff is like, I got this IEEE standards. I can either do 64 bits or 32 bits. And if I do more bits, that means slower computation, higher precision, okay? And the vague intuition is that, like, since my machine learning stuff is already mushy, it's like not correct all the time, something % of the time. You know, we are like basing off of like good enough. Since I am at operating this level, let me make it even less precise, go from 64 to 32, maybe even less, but just compute quicker, right? Of course, then you have to think about, am I still getting something real, a little bit reliable or total garbage or not? Okay. Now, luckily, this is new in machine learning, people are thinking about it. For this type of stuff, people have thought about it and worked on it for decades. We have numerically stable algorithms for this type of thing, okay? And we have a notebook on our canvas doing this QR. And my basic punchline is, as soon as you have QR, you solve your projection, okay? And we will do even maybe faster stuff than this. We will see. So far, so good. I have about like 15 minutes left, and I want to do a little more. Any questions? Okay, now let me connect this stuff to some algorithms you probably have heard of. Then I'll get back to what I was gonna do later. All right. Okay. This is good old linear regression. If you're working on a sensitive subject like healthcare or maybe some parts of finance, only a few algorithms are allowed, and this is one of the few. Okay, this is something we understand pretty well. Because these are the industries that are regulated. Let's say you make a decision in terms of somebody's health insurance premium, then there is some regulation that you need to be able to explain. Then you just cannot say, I run a 100 billion parameters deep. This is what it spit it out. No, that's why. Otherwise, in many industries, of course, people would like to use state of the art. All I was trying to say is this is something we think as humanity we understand well, and we are using it in even very sensitive fields. Okay? Yeah. Man, I have just an hour and 15 minutes to talk about a lot of stuff. For this, come to office hours or go for a coffee. We can talk. I'm happy to talk to you guys about any nerdy topic. Just not now. Okay. Okay. Fine. Sorry. Okay. Now let me go to linear regression. What is linear regression? In the basic version of linear regression, you will have labeled vectors. Okay. It's going to be supervised situation. There will be vectors, and then usually there will be just one value attached to them. Suppose you're modeling, say, house market. Okay. Every house will come as a vector, whole bunch of features. And then, of course, next to it, you want to predict how much it's worth. That's all. Okay. Or many other situations. You have a vector x. This xi has a whole bunch of coordinates, all the features. This yi doesn't have any coordinates. It's just one number right there. Okay. And we want to have a model that tries to predict this as good as possible. But we are insisting on the model being linear. I will tell you what linear means precisely. That's the goal. All right. And then in other words, we want to find a function f that is linear that goes from this n features to a number, and it fits your data the best. Okay. So whatever the best means, we'll get to that as well. All right. Okay. So for now, I did not say two things precisely. What do I really mean by linear here? Second, what do I mean by the best fit? Okay. Other than that, I said reasonable stuff. Okay. So let's try to do the best a little better. For us, the best will be given by, for the moment, we will see variations of this during the course, by the squared error. My function f is predicting a number. I'm taking it minus from the actual thing, square it, sum them up. That's my error, okay? Squared error of my function f. And I would like to find the f among the linear options that is minimizing this error, like the best one in terms of this error. That's my notion of the best, okay? That's sometimes called squared error. Okay, fine. Now, what do I mean by linear? Well, when people don't tell anything more, when they just say linear regression, what's meant in this context is usually this. Take every feature, multiply it with some number, and you're allowed to add a number at the end, which is not multiplied with any feature as well. So you're literally trying to predict this weights the best you can. And this is sometimes called bias. I'm kind of shifting towards some number. Okay, that's what linear means in this case. So our model is literally my yi numbers are going to be given by data features multiplied with this weights, added with this bias. That's my model now. Okay. And there's a little trick to make it look nicer. People would usually do the following. They would say, these are your features. After every single data vector, add a 1 to the last coordinate. And then put that W0 thingy, the bias thingy, to the last coordinate of your weight vector as well. When you dot product these two, you will end up getting what is written there. This times that plus this times that, blah, blah, blah. This one is cooked up so that you get this omega 0 at the end, okay? And they will say, okay, this is my model now. I'm trying to fit my data head, which means at the end I add a 1, multiplied with my weight stuff, this omega, minus from the actual value, that is the label, that is the correct ground truth, squared and summed up. I want to minimize, I want to find the best omega possible so that this entire number is a small number, as small as possible. That's my target, okay? Now, even more concisely, these are my, say I got, say, capital N many data points, and every data point's got little n features, and I added 1 at the end. If I stack them up all together, they're gonna look like a big, gigantic matrix, which is having little n plus 1 rows, and as many data, as many columns. Every column is 1 data point, okay? And this is the labels I got. First column corresponding to first label, second column, second label, right? And what I'm trying to do is actually, if you think about it, I'm trying to write this guy in terms of this thing transposed multiplied with that weight vector. That's what I'm trying to do, okay? If you transpose this, the dimensions will be what? What is the dimension of X transpose? Let me write it here. It is capital N times N plus 1. And the dimension of weight is N plus 1. And dimension of Y is N. And what I'm trying to say is to find the best omega, the weight vector, so that this matrix times the omega gets as close to this vector as possible in terms of this error. That's what I'm trying to do. And what does it mean? Well, this is given to you. This you get to pick. This is also given to you. What you're actually trying to do, look at the span of your rows of X or columns of X transpose and find the best omega so that this thing gets closest to your Y. In other words, you're trying to do a projection. Okay? That's about it. So you're trying to project your label vector on the span of your data stuff. That's linear regression. Okay? That's what it is all about. So if you would do X transpose equals QR, like our QR decomposition, then your weight vector will be just this. This is the projection, as I said, QQ transpose times Y, and you'll be done. Okay. Okay. Let me see. I still have 5 minutes. That's good. Yes. What is QQ? Go ahead. I couldn't hear. It's the squared error. That's usually what they use. It's not something I personally prefer, but if you see it elsewhere, I don't want you to get confused. It literally means label minus your prediction squared and summed up through all your data. Okay, squared error, that's what it means. Yeah. Okay, now, if I would be able to do this QR decomposition of my given data, X transpose is my data matrix. Do the QR, then QQ transpose will be your projection. This is your label vector. Just do projection and you'll be done, okay? So this is all correct and true. However, your data matrix is gonna be probably gigantic. You may not want to do the QR decomposition of a gigantic matrix, okay? So you will do other things that will get you the same result, but not do the QR, maybe something cheaper to do. You wanna get the same thing mathematically, same answer, but maybe algorithmically more clever, okay? And that's usually what you would do. You will do some sort of gradient descent on the loss function, blah, blah, blah. We will get to those later in the course. I can tell you later. But for now, this is what linear regression is. Okay? You're just projecting your label vector on the span of your data stuff, essentially. That's about it. And then people would read this weight vector afterwards. Now, when you compute this omega, what was the point of this omega? Now I'm thinking my yi is like, first coordinate, first weight of this times my first coordinate of my data, Okay. After you look at this, you will say the reason that is allowed in like a whole bunch of regulated industries is that it's kind of interpretable. You will say, okay, if this number is much bigger than this, then you'll say, okay, that means the first feature is much more important than the second one for my model. It's very easy to interpret. Okay? It's not black box. You just look at the numbers there. Which one is bigger? That means your model is thinking that feature is much more important. Okay, now that's one part. And the second part is, let's say you did this, you run your computation, you get your omega done. How do you assess the quality of your model? One standard thing people do is something called R2 score. And it's going to be in the notebook that you will see today on Canvas. There are some standard stuff that people agreed on to assess the quality of your linear regression. That's not a big deal. It's very standard. You will see it written. Play with your stuff. Very good. I have about 3 more minutes. And in that 3 minutes, let me decide what to do. Okay, maybe just warm you up for the PCA. Next thing we would like to do, again, using projections, will be this PCA. And I'll just say what it is, then we'll be done. I only have 2 more minutes or so. So what's the goal in PCA? You again have a lot of data points. And suppose this time they have too many features. This little n is not so small, okay? And you'd like to reduce the dimension of them, but still somehow respect the structure of data. How much you would like to reduce is something you get to decide. Suppose I want to go from n dimensions, say this is like 1,000,000 dimensions, to say 100 dimensions, okay? N is where your data lives, the number of features it's got, and D is something you get to pick yourself. I want to reduce the dimension of my data from this big one to a small one. What I want to do is like, I want to find something like that plane. It was 2D. I want to find the best D-dimensional fit to my data. That's what I would like to do, okay? In other words, if this is my data, and if this represents the projection matrix that wasn't so easy to compute, projection on that L, this is a projection. The difference is how much you're missing. Sum up those and minimize the error. That's your goal in PCA. Question or no? Okay, people are just stretching. Okay, so that's the goal of the PCA. You would like to find the D-dimensional space L that minimizes this error. Okay, and we will end up seeing this is given to you by singular value decomposition. That's going to be next week. Thursday, we have our first guest speaker. He's coming from Wells Fargo. Wells Fargo moved a big part of the team from San Francisco to San Antonio like a year or so ago. And they started hiring a whole bunch of technical people. So this is one of those people there, I think a lead data scientist. He will talk about causal inference. Like you want to do some model which respects cause and effect, basically, not just some random, machine learning stuff. So that's what we do Thursday. Next week, we will go from here. Thank you so much.